All right, so these next couple of results are actually going to be looking a little bit into the world of trying to do some operations on different types of congruences. So this first statement is actually going to be chatting about this notion of addition. So what's going to happen is that you're going to give me two random integers. So in this case, a and b. What's going to happen is that that first number a is going to have the property that is going to be congruent to 2 modulo 6. And that second number, in this case this number b, is going to have the property that is going to be congruent to 4 modulo 6. What I'm claiming in this situation is that when you add these two things together, so in this case computing a plus b, that this new object is actually going to be congruent to 0 mod 6. Okay, so before we dive too far into actually trying to show this thing, let's do a few examples so we can kind of really see what's going on kind of underneath all of this, and then we'll dive into the very formal structure of what does it actually mean to be congruent to blah and congruent to the, and then pushing all those random symbols around. So in this case, I want to think about coming up with a whole bunch of little numbers a and b that both happen to be congruent to 2 and 4 respectively, and then trying to actually compute the sums of these two things. So in this case, the easiest numbers that are probably going to be congruent to 2 and 4 are going to be just the numbers 2 and 4. In those cases, I have something that is most certainly going to be congruent to 2 mod 6 and something that's also going to be congruent to 4 mod 6. And if I compute the sum of these two things, I'm going to get 2 plus 4, and that's going to add up to a 6. And in this situation, I know that 6, if I divide it by 6, is going to give me a 1 with a very nice remainder of 0. In this case, I know that 6 is going to be congruent to 0, in this case modulo 6. You can also see this idea that 6 divides 6, and we had that earlier result that says this notion of being congruent to 0 is also going to be the same as saying this notion of divisibility. So in this case, what I'm hoping to see is all of these little numbers, a plus b, are always going to be divisible by 6. If we have a divisible by 6 property, I know that I'm going to be congruent to 0 mod 6. So in this case, let's come up with a few other numbers. Let's say I up the power from 2 to an 8 in this case. I know that 8 is actually going to be congruent to 2 mod 4. There's a couple ways you can see this. The first of which is you can take 8 and divide it by 6, which is going to give you a 1 with a remainder of 2. And the idea is that this 8 looks like 6 plus 2. So there's a little 6 hiding inside of that, and there's this extra little bit of 2. So I have 8, which I know is going to be congruent to 2 mod 6. And I'm going to, let's say, I don't know, choose, let's up this by 6 as well. So in this case, let's look at 4. In this case, 4 plus 6 is going to be a 10. So it's 6 plus 4. In this case, I have this nice number that is again going to be congruent to 4 modulo 6. And if I compute the sum of these two things, let's say 8 plus 10, what's going to happen is that this thing is going to kick out an 18. And 18 in this case is going to be divisible by 6. So I do in fact have that this thing is going to be congruent to 0 mod 6 again. The idea is that 18 is simply just going to be a 3 times a 6. And that's where my 0 is going to come back again. So I have this idea that that number that was kicked out is going to be divisible by 6, therefore that whole sum is going to be congruent to 0 mod 6. Okay, so let's look at something that may be going to have some negative signs in. So in this case, I added a 6 to 2 to give me something else. Let's say I started at 2, but I subtracted a 6. So in this case, if I'm looking at the number negative 4, which in this case, what's going to happen is that 4 is actually viewed as a negative 6 plus a 2. So it is still going to have this very nice property that it's some 6 hiding in there with this 2. So I'm still satisfying this congruent to 2 mod 6 condition. And then let's say, let's just keep on using the 4 from up above. In this case, it's actually going to be really nice. So what I'm looking at is I'm looking at negative 4 and I'm looking at 4. And if I add those together, what's going to happen is that just gives me a 0 directly. And I know that 0 is going to be congruent to 0 mod 6. So everything is good in that case. So in all three of these situations, it does appear that the sum of these two things, this a plus b, is constantly kicking out something that's going to be 0 mod 6. So what I want to start to do is I want to start to think a little bit about why this might actually be true. So what's happening in this case is really just an application of what does the definition of this say and what does the definition of that say. So the idea is that if you're going to be congruent to 2 mod 6, what's going to happen is that your a is going to look like some integer multiple of 6. So I'm going to have this 6 times k plus a 2. And that's exactly what these things back here were looking at. It was 6 plus 2 in this case. This was a 6 times a negative 1 plus a 2. But at the end of the day, there was always this little 2 broke off at the very end. And that last thing, this idea of what is b going to look like, well, b is going to be some integer multiple of 6, but with 4 extra added to it. So in this case, I'm going to say that b is going to look like some, in this case, 6l. I'm going to use a different variable name in this case, but then a plus 4 at the end. So what's going to happen then in this situation is that when I add these together, so a plus b is going to be 6k plus 2 plus 6l plus 4, well, you can see all of these nice little 6's popping out. You can see that all of these little pieces are going to have a 6, and if I factor out a 6 out of that thing, I'm going to be left with a k plus an l plus a 1. So the idea in this situation is that up here that k and l are going to be integers. And what's going to happen is that this little object right here is again going to be some very nice integer. So at the end of the day, this is going to look like 6. That's not a 6. It's going to look like 6 times some integer. And that's exactly what I want to say if I'm going to actually be congruent to 0 mod 6. I want to get something that is going to be some integer multiple of 6. It's again this idea that a plus b is going to be divisible by 6. And there's that 6 that I'm looking for. So this next slide, I'm just going to kind of show you, and if you're interested in actually sketching out all the details, you can pause the video to kind of sketch all of them. So this is going to be one of these classic no-show tables that really just kind of formalizes what I just got done showing on that last slide. The idea is that if you start with this notion of being congruent to 2 or congruent to 4 modulo 6, there's going to exist some integers k and l such that a is going to have this representation and b will have this other representation. And when I add those two things together and do a little bit of factoring, I get right down to that world of looking like 6 multiplied by k plus l plus 1. So in this situation, that little k plus l plus 1 is in fact going to be an integer. This is officially using this closure of the integers property. This idea that I just have a sum of 3 integers occurring, in this case k plus l plus 1, all integers, that final result is still going to be an integer. Therefore, this whole kind of expression a plus b looks like 6 times something. In this case, I represented that something as an h, which is to say that a plus b is going to be 0 mod 6. So what can happen then is I can take that notion and I can slowly try to write this up a little bit more cleanly. So in this case, I'm going to convert this thing to one of these nice kind of paragraph representations or paragraph proofs that I really want to start to justify what's going on. So in this case, I'm going to take this idea of what this no-show table said, and I'm going to transition it into a paragraph. So here's where I'm going to say, I'm going to assume that a and b are some integers. They're going to have these really special properties that, in this case, a is going to be congruent to 2 mod 6, and b is going to be congruent to 4 mod 6. I'm going to use this notion of what the definition of this actually means. So in this case, by the definition of congruence modulo 6, they're going to be these magic integers k and l, such that a and b have this very special representation. And then I'm just going to let the reader know that I'm about to do some addition. So in this case, adding a and b together and doing a little bit of math magic is going to say, hey, a plus b is going to look like this nice 6 times something. That something is in fact going to be an integer. Therefore, I'm going to have that a plus b is going to be congruent to 0 mod 6. So in this case, it's actually a pretty nice little write-up. It doesn't take very long. I actually think it's a little bit easier to kind of read than this giant truth table. I'm not a huge fan of these truth tables for actually kind of representing something, but they're a really good tool for actually kind of building up the actual argument that you want to look at. So I'm actually going to just really briefly chat about the next property. I'm going to leave most of this up to you to go kind of take a peek at the filled out notes. The idea is that that first example was going to be talking about what happens when I add those two numbers together. What I want to think about next is what happens when I multiply these objects together. So first off, I'm going to be looking at just a couple examples. So in this case, a and b. In this case, what happens when I compute the product of these things? Well, in this case, let's take those same examples. So 2 and 4. If I multiply 2 and 4 together, I'm going to get, in this case, an 8. And I know that 8 in this modulo 6 world is actually just going to kick out a 2. What ends up happening is that if I take that 8 and just subtract 6 from it, I'm going to be left at a value of 2. The notion that 8 is going to look like 6 plus 2. So in this case, 8 is actually going to be congruent to 2, in this case, modulo 6. So it seems to be working in this case that I can multiply these things together, and in this thing is going to claim that it's going to kick out a 2. Let's look at another example in this case. I think we upped this one up to, let's say, well, let's look at the negative one. So the negative 4 in this case. The negative 4 and the positive 4 in this case, when I multiply those together, so negative 4 and a positive 4, that's going to kick out, in this case, a negative 16. And what's going to happen in this case is that that negative 16 is also going to introduce a 2 in this modulo 6 world. Because what's going to happen is that negative 16 is going to be viewed as a negative 18 plus a 2. And that negative 18 is simply just a 6 times a negative 3 plus a 2. The idea is that I can take that negative 16 and add 6 a couple times. So negative 16, I add 6, I add 6, and I add 6 3 times in this case. It's going to bring me out of this hole of being at negative 16, ultimately leading me up to this world of being 2 modulo 6 again. So in this case, you can still see this example of kind of doing this multiplication of a couple different things. In this case, what it's going to happen is that it's actually going to kick out a 2. So it doesn't matter if I take a 2 and a 4 to start with, or if I take this -4 and this 4. So what's going to happen is that when I try to show this result, I'm not going to have to add a and b together. Rather, I'm going to have to multiply these things together. So what's going to happen is that you're going to be looking at this a, which is going to look like some 6k plus 2, and this b, which is going to look like this 6l plus a 4. And if I do this multiplication of these two things, here's where I got to actually do a little bit of algebra. All right. Okay, if I expand this whole giant mess out, what's going to happen is that the 6k times the 6l is going to turn into a 36kl. The outside part is going to be a 6k multiplied by this 4 in this case. So the 6 and the 4 is going to give me a 24, and it's going to pick up a k. And the inside part is going to be the 2 and the 6, which is going to turn into a 12 with an L. And at the end of the day, I'm going to get the 2 and the 4, which is going to introduce an 8. So what I'm hoping to see is, I'm hoping to see a whole bunch of little 6s so that I can kind of factor out this big 6. And what I want left over is some little 2 tacked on at the very end. And it's exactly this step that we did up here where we saw that 8 represented as a 6 plus a 2 that makes this whole thing work. What's going to happen is I'm going to write everything else the exact same except for that very last step. What I'm going to do is I'm going to view this 8 as a 6 plus a 2. So here's the little 2 that I'm hoping to see. That's the 2 that I want. Everything else that's out in front of this thing actually has a multiple of 6 hiding in it. The idea that all of these things are going to be congruent to 0 mod 6, and I'm just going to be left with this little 2. So in this case, if I factor out a 6, I'm going to have a 6kl plus, in this case, the 24 divided by 6 is going to bring me back to that 4 with a k, and then I'm going to have a 2l, and then plus a 1. And at the end of the day, I'm going to have a little 2 afterwards. So what's going to happen is that I'm going to get 6 multiplied by something that is an integer, and then at the end of the day, I'm just going to have a 2. So that is to say that this product is actually going to introduce a 2 modulo 6. So just like before, I'm just going to quickly glance over the actual no-show table for this thing. It actually has the slightly nicer representation that I'm kind of able to not have this horrible chicken scratch that I did on the last slide. But in this case, you can kind of see that multiplication occurring. So the idea is that you again start with this representation for a and b. You do the multiplication. We get all the way down to the stage that we have this 8, but I want to see a 2. So I break that 8 into a 6 plus a 2, factor a 6 out of everything except for that last part. I'm going to have a little 2 left over, which is going to say that AB is going to be 6 times stuff. In this case, that stuff is an integer. And then I'm going to have a little plus 2 afterwards, which is to say that I have this representation of AB equals 6h plus 2. Therefore, AB is going to be congruent to 2, in this case, modulo 6. I got a slight typo in there. I'll fix that and go from there. And just like before, I'll quickly just show the kind of nicely written up version of this thing. If you're interested in sketching out all these arguments, you can pause this again to kind of fill in the details. What I did is actually just copy and paste the last proof that we had. If you actually go back 2 slides, I have the exact same proof here, except for I replaced the word multiply, or I replaced the word add with the word multiply. And at the end of the day, I also had to add 1 extra line of the algebraic step, but at the end of the day, it all works out the exact same. So I'm going to have this notion that if you multiply these things together, do a little bit of stuff afterwards, I'm going to kick out this property that AB is going to be 2 modulo 6. So what we're going to be doing in the next video is actually going to be looking at that exact same result, except for what's going to happen is that I'm not going to just keep these kind of A's and B's with specific numbers. I'm going to replace the 2 and the 4 and the 6 with very general letters. So the idea is that all of these proofs are going to be the exact same, and they become very tedious. I don't want to constantly have to redo this over and over and over again. What I'd rather do is actually have the ability to say, if you give me just 2 random numbers that are congruent to blank or blank, I can easily compute the product. It doesn't take me any time at all. In this case, all it depends upon is that very special values 2 and 4. When I multiply those together, I got an 8, and I know that 8 is going to be congruent to 2 mod 6, so I'm done. So the idea is that I can switch the 2's and the 4's and the 6's, and that result's still going to hold. You're just going to have to see what your new product actually ends up kicking out. So in this case, this is the slightly easier one because it's less kind of random letters and variables all over the place. I can see the 2's and the 4's and 6's pop up. What's going to happen in the next one is you're going to have a whole bunch of kind of letter salad in this case. So it becomes a little bit more obnoxious to look at. So if you get confused in that one, just jump back to this example and you can see where all of those little pieces all come back into play.